going to switch gears a little bit today and talk about some area problems, but eventually we'll connect these area problems back to our antiderivatives. So I'm going to start by just doing an example. So we've got the function 4 minus x squared, and I've sketched its graph over to the right. It's a parabola because of the x squared. It opens down because of the negative, and it's been shifted up 4 units. In this problem, our goal is to find the area under that curve, between the x-axis and that curve, from x equals 0 to x equals 2. And so I've shaded that region in green. What we're going to do to find the area here is we are going to draw some rectangles. Specifically, the problem asks us to draw 4 rectangles. And so we've got a region that has a width of 2 units, from 0 to 2. And so if we take our 2 units and we divide it by 4, that gives us a half. So the width of our rectangles is going to be 1/2. So I'm going to take this region and just divide it into 4 segments of equal width. Then I'm going to turn each of these segments into a rectangle because I know how to find area of a rectangle. And when it says with left endpoints, they mean take the left side of that rectangle and extend it horizontally. And so I've drawn in purple 4 rectangles using the left side to create the top of that rectangle. Now I can see in my picture this is actually going to be an overestimate of area because my rectangles are kind of going over that shaded region, but it'll still give us a nice estimate. Okay, so area of a rectangle is length times width. The width of each rectangle is 1/2 unit. And to find the length or the height of the rectangles, we are going to evaluate the function at those left endpoints. So the height of that first rectangle, which I've denoted as h1, is going to be whatever the y value is at x equals 0. I can see on the graph, or I could plug 0 into my function, that that y value is 4, and so the height of that first rectangle is 4. The height of the second rectangle is whatever that y value is when x is 1/2. I can take 1/2 and plug that into my function, so 4 minus 1/2 squared. I put that into a calculator and got 3.75. My third rectangle, I plug in 1 into the function. 4 minus 1 is 3. And for the fourth rectangle, I'm going to plug 1.5 into the function, and I got a height of 1.75. So to find the area of this region, I basically have to add up the area of these 4 rectangles by taking the width times each of their heights. Or another way of writing this, I could actually factor the w out. So another way of doing this area problem is I could just add up all of the heights and multiply that by the width. And that's exactly what I'm going to do here. So I add up all the heights, I multiply by 1/2, and I got 6.25. This is just an estimate for the area, and again, as we can see, this is actually going to be an overestimate. Now, I chose to use the left side of each rectangle to create... Now, I chose to use the left side of each region to create my rectangles. I could use the right side, the right endpoint, to create my rectangles. And this time, the rectangles are actually going to be under the curve, and this will give me an underestimate. So let's do this next. Let's, same region, try to find the area using right endpoints. So my width is the same. The width is still 1/2, but my heights are going to be a little bit different because I'm using right endpoints. The first one, we're going to take the function evaluated at 1/2, the right side of that rectangle. The second one would be at 1. The third one would be at 1.5, and the fourth one is now going to be f of 2. F of 1/2 is 3.75, f of 1 is 3, f of 1.5 is 1.75, and f of 2 is 0. And then I can do the exact same kind of computation. I'm going to take my width, and I'm going to multiply that by the sum of all of my heights. And this time I got an area of 4.25. Notice the number's a little bit smaller because now we're talking about rectangles that are under the curve. This is actually an underestimate. The actual area is somewhere between those two numbers that we found. Finally, we could use the midpoint of each region to create the height of our rectangles. I redrew my picture. You don't have to do this. But for that first rectangle, which goes from 0 to a half, the midpoint would be at a fourth. And I could do that for each one of these rectangles. And as we can see by the picture, this is probably going to be a much better estimate of this area because you can see the rectangles, part of it is kind of under the curve, part of it is over the curve. So this will give us a much better number. Okay, the width of my rectangles hasn't changed. It's still a half. For my heights now, the first rectangle, halfway from 0 to a half is a fourth, or 0.25. The second rectangle goes from, x equal half to x equal 1. Halfway through that is 3/4, or 0.75. From 1 to 1.5, 1 1/4 is the halfway. And from 1.5 to 2, 1 3/4 is the halfway. And so I'm going to plug all of these x values into my function to get my heights or my y values. I used a calculator to help me with that. And then finally, to find my area, I take my width, which is 1/2, and I'm going to multiply that by the sum of all of these heights. I put this into my calculator and I got 5.375 as my estimate for area. Now this is still not the exact area. We're just using rectangles. It's just an estimate for the area. But if I were to increase the number of rectangles, I would get a better and better estimate. And in fact, if we let the number of rectangles go to infinity, if we're somehow capable of drawing an infinite number of rectangles, this sum is going to become the exact area. And the notation we're going to use for area under the curve is something called a definite integral. It looks a lot like our indefinite integrals, except there's going to be numbers on the top and the bottom of that integral sign. What this notation means that I have written down for the definite integral is the area under that function from an x value of a to an x value of b. That's what this notation means. Just as a side note, where the notation comes from, the integral symbol is kind of like an S for sum, and it's basically saying you're adding up the function values, which is the heights, and you're multiplying that by dx, which is actually the width of the rectangles. So just as a side note, that's where that notation comes from. All right, so let's do another area problem, but this time we're using that new integral notation. So this problem is asking us to find the area between the x-axis and the function y equals 1 over x squared from, and the little numbers on the top and the bottom tell you, from x equal 1 to x equal 5. Okay, so if we are dividing this region into 4 rectangles, we have a region that has a length of 4. 4 divided by 4 rectangles is 1, so the width of each of my rectangles is going to be 1. This problem says we are using left endpoints to create our rectangles, so it's going to be an overestimate. So the height of my first rectangle I will get by plugging in x equal 1. That's where the region starts. If I go over 1, then I'm at x equal 2, x equal 3, x equal 4. I take these x values, I plug them into my function, and I get y values of 1, a fourth, a ninth, and a 16th. Then to find the area, we take the width, which is 1, and we multiply that by the sum of all of those heights. I put this into my calculator, and then I rounded to the nearest hundredth, and I got an area of approximately 1.42. Now, in some cases, we'll be able to find our definite integrals using geometry, because we'll have functions that are less complicated than our previous examples. So 3a This definite integral is asking us to find the area under y equals 5 from x equal 1 to x equal 4. So the very first thing I'm going to do is I'm going to draw a graph. Y equals 5 is a horizontal line that goes through 5. I want to find the area from x equal 1 to x equal 4. And so the region we're talking about is a rectangle. And now that I have my picture drawn, I can see that the width of this rectangle from 1 to 4 is 3, and the height of this rectangle is 5. And so the area is just length times width, or 15. So this integral equals 15. In example B, we want to find the area under the curve y equals x from x equals 0 to x equals 3. So once again, I'm going to start by drawing a picture. Y equals x is a line with a slope of 1 and a y-intercept of 0. So it goes through the origin, and then I go up 1, over 1, up 1, over 1, and there's the graph of y equals x. We want the area from x equals 0 to x equals 3, and so this is the region we're talking about. We are talking about a triangle. I can see in my image that the base of this triangle from 0 to 3 is 3 units, and the height of the triangle should also be 3. If it's hard to tell on your graph, if your graph is a little bit sloppy, how do I know the height is 3? Well, if I plug x equals 3 into this function, I get a y value of 3. So this right endpoint is at 3, 3. Area of a triangle is 1/2 base times height. So in this case, area would be 1/2 3 times 3, or 9/2, or 4.5. And that's the exact value of this definite integral. All right, let's do one more. In this last problem, we are trying to find the area under y equals x plus 1 from x equals 2 to x equals 5. And so once again, to do these problems with geometry, I have to draw a picture. This is another linear function. It has a slope of 1, and this time we have a y-intercept of 1. So y-intercept of 1, up 1 over 1, and there's the graph of this function. I'm interested in the area from x equals 2 to x equals 5. So this time I'm talking about actually a trapezoid. I'm going to label some points because I think I was a little bit sloppy with my graph. So if x is 2, 2 plus 1 is 3. So this should be the point 2, 3. And if x is 5, 5 plus 1 is 6. So that should be the point 5, 6. Now I don't remember the formula for area of a trapezoid, but that's okay. I am going to take this region and I am going to divide it into a rectangle and a triangle. And so we'll start with this rectangle here. The width of this rectangle from 2 to 5 is 3, and the height of this rectangle is that y value of 3. So area of the rectangle is going to be 9. Then I'm going to find area of this triangle up here. The base of the triangle is 3. The height of the triangle, it goes from y equals 3 to y equals 6, and so the height is also 3. So area of that triangle, 1/2 base times height, is going to be 9/2 or 4.5. And so then my total area, which is going to be my final answer, would be the sum of those two things, or 13.5. All right, that's it for today. Let me know if you have any questions.